Hello and welcome. Now, in a previous video, we took a look at the n-dimensional coordinate system. Now, in that video, specifically, we were looking at the Cartesian coordinate system, which is a natural extension of our x and y axes. We just take a certain number of steps in x and a certain number of steps in the y direction, and then we just add in the z-axis and take a certain number of steps in the z-axis to arrive at a point in three-dimensional space. But what if there's another way? Well, we've already seen in two dimensions that rather than having our x and y axes, we can throw those out the window and use an angle from a polar axis and come up with our polar coordinate system. There we're taking a look at an angle from the polar axis, which aligns with the positive x-axis. And with that particular angle from 0 to 2 pi radians and a distance, we can also arrive at a point on the xy plane. What if we were to take that concept of polar coordinates and extend that so that we can get into our third dimension? Well, let's take a look at how we could extend that. There's more than one option. Rather than using our Cartesian coordinate system, which gives us ordered triples, x, y, and z, what if we started with the ordered pairs from the polar coordinate system, r, theta, and then come up with a way to create points in the third dimension? Well, the easiest way to do that would simply be to borrow our z-axis from the Cartesian coordinate system. We call that the cylindrical coordinate system. So we have these ordered triples, r theta, which come from polar coordinates, and z, which is borrowed from Cartesian coordinates. It's a bit of a mix of both. Remember that on the polar coordinate system, our polar axis aligns with the positive x-axis. That's labeled here as r, and r is going to be a distance measured from the origin. We can usually take r to be a positive number. And theta is an angle measured from that polar axis counterclockwise, typically from 0 to 2 pi. That will give us a unique point for any given r and theta. What we'll do now is we'll take that xy plane, put that into standard first octant view, and align our polar axis. So now, in the cylindrical coordinate system, we have a polar plane that we can see here kind of corresponding to the xy plane. And then we also have z. And that will allow us to get that third dimension that we need. Since it's a combination of sort of these circular coordinates from polar coordinates, as well as a straight line coming from the z-axis, you can kind of understand why it's called cylindrical coordinates. Now, since we already know how to convert between polar coordinates and Cartesian coordinates from a previous video on polar coordinates, the conversions between cylindrical coordinates and Cartesian coordinates in three dimensions are basically identical. X corresponds to r cosine theta, y corresponds to r sine theta, and you can see that just by constructing a triangle on the xy plane. We also know that x squared plus y squared is equal to r squared from that same triangle, and tangent theta is equal to y over x. We'll have to maybe be careful about which of the four quadrants theta is actually in. Since we are now in three dimensions and borrowing the z coordinates from Cartesian coordinate system, in cylindrical coordinate systems, we have exactly the same value for z. There's no conversion necessary. Z is equal to z in either coordinate system. Much like with polar coordinates, it's often the case that r is positive or 0, and theta is between 0 and 2 pi. Now that we've got this conversion formula, it's easy to get from one to the other, but you can imagine that's going to change the shape of a lot of common graphs. They're not going to be the same shapes anymore. Why don't we take a look at a couple examples of basic graphs in cylindrical coordinates, and it might give you a sense of where the strengths of cylindrical coordinates are, what kind of shapes become easier in that coordinate system. Let's start off with a basic equation, r equals a constant. We can call this constant radius, let's say. R is the distance measured from the origin on the xy plane, but you can also think about r as basically just being the distance away from the z-axis perpendicular to the z-axis. Let's also assume that theta is from 0 to 2 pi, and z could be any real number. Why don't we just choose a value for z? Make it easy, let's let z equal 0. If that's the case, then our graph would exist on the xy plane in Cartesian coordinates. That's our polar plane. If you remember, on a polar plane, if r is equal to a constant, then that gives us the graph of a circle. there's our circle r equals c, so that's our radius of c, and at z equals 0. Okay, well, if z could be any value we like, why don't we let z equal 2, for instance? Okay, well, that's going to shift our circle up by 2 units. And we're not necessarily limited to a positive value of z. We could let z equal -3. Well, that's just going to translate that circle down 3 units. And you can kind of get a sense of what the shape looks like. We've actually seen the shape already in a previous video on cylinders and quadric surfaces. This is a circular cylinder. In fact, it's a right circular cylinder centered right at the z-axis. This is assuming that c is non-zero. Let's also assume that c is a positive value. That will just give us the radius of this circular cylinder. Okay, well, if that's what r equals a constant gives us, what if we were to let our next variable equal 0? Maybe let's let theta equal 0. Sort of like a constant angle. Let's assume that r is greater than or equal to 0, and z can again just be any real number. Best to start off with z equals 0, and remember what that kind of graph looks like on our polar plane. If theta is equal to a constant, then that gives us a straight line. If r is greater than or equal to 0, then that gives us a ray pointing outward from the origin. Then we can take that particular ray and translate that to any value of z that we like. We could shift that ray up 3 units, or we could shift that ray maybe down 2 units. And with all of these possible translations up or down the z-axis, you can see that this will create a set of points that are right above one another. It forms a vertical plane. But it's actually not a full plane, it's really only a half plane, assuming that r is going to be greater than or equal to 0. Okay, well, we've taken a look at r equal to a constant, theta equal to a constant. What about if z is equal to a constant? Well, that's not quite as interesting since we already kind of know what z equals a constant would look like in Cartesian coordinates. It's not really that much different except for the fact that our grid system, instead of an xy grid, is a polar grid. When z is equal to a constant, you can imagine that this is a constant height above the polar plane. So we construct a plane parallel to the xy plane. With these couple shapes in mind, you can see one of the big strengths of cylindrical coordinates right away, the ability to create this cylinder with such a simple equation. So let's list that as a main strength of cylindrical coordinates right away. Right circular cylinders that are centered on the z-axis. What might not be immediately obvious is another shape that is very easy to express in cylindrical coordinates but difficult in Cartesian coordinates. And that shape would be a cone. Specifically a cone whose central axis is the z-axis and having a vertex at the origin. The equation for such a cone is a basic linear equation. Z equals a constant times r. Let's let z equal k times r with k not equal to 0. To see how this creates a cone, let's take a look at our z-r axis. It's a little strange, but our z-axis and our polar axis. You can imagine that this is just like the xz axis, since the polar axis are points in the same direction as the positive x-axis. As an example, let's let k equal 2/3. We should see that that's a linear equation and that k is actually just the slope. We have a line passing through the origin with a rise of 2 and a run of 3. Now we're going to take that line and remember that theta is sort of our free variable. It can be anything from 0 to 2 pi. When we want to try to graph this in 3 dimensions, the line here that we've just drawn might be corresponding to theta equals 0. If we were to let theta range from 0 to 2 pi though, then we're going to be rotating around the z-axis counterclockwise, a full rotation. That line, when we rotate around to theta equal pi over 2, would exist in our yz plane, and then when rotated around to theta equal pi would be back in our xz plane, but it'll be reflected since we've done this rotation of 1/2 of a circle. And then rotating it all the way back around, we complete the other side of the cone. A little shading here might help you to try to visualize that. And there we go. That's one of our other big strengths of cylindrical coordinates. right circular cylinders and cones centered on the z-axis. You probably notice that when I say cone here, I actually mean I have both an inverted cone and a right side up cone, just depending on what values of z we wish to use. If z is a negative value, then we actually have a right side up cone. If z is a positive value, then we have an inverted cone. But the two pieces collectively known as a cone here. Why don't we take a look at the graph of this cone in 3 dimensions, a little easier using Maple now. I'm going to use the plots package, and with plots, it's going to include a whole bunch of new plotting tools, including the plot 3D command. And I'm plotting z equals 2/3 r from -2 to 2, and yeah, it's a bit weird to maybe use a negative value of r, but that's because I want to have negative values of z. And then let's say we want to go from 0 to 2 pi for theta. Now, the moment you graph that, it doesn't look like a cone at all. And that's because this is actually just the equation of a plane using Cartesian coordinates right now. It's actually using a perpendicular r and theta axis, just like we would try to use a perpendicular x and y axis. So this isn't going to be very useful at all. We have to go and specify that we want to use cylindrical coordinates. We'll add an extra parameter at the end. We're going to add this extra command, coordinates equals cylindrical, or simply just chords for short. All right, well, if you try that, you're going to find something doesn't look quite like a cone here still. Well, this is a very common mistake. You're going to have to make sure that when you're using cylindrical coordinates, that you do specify the r and theta axes in the correct order. You can see here I have changed the order, theta from 0 to 2 pi first, and then r from -2 to 2. And let's see. There's our classic cone now. You'll notice as well that with Maple, if you're using cylindrical coordinates, you actually get to see these beautiful circular cross sections parallel to the xy plane, or parallel to the polar plane. Whereas trying to graph some kind of circular shape like this, like an elliptic paraboloid, for example, in Cartesian coordinates, oftentimes it doesn't really graph it quite as nice as using these new coordinate systems. It's naturally designed for sort of circular shapes like this, something that has a circular symmetry. Now, as I mentioned earlier, there's more than one way to extend the polar coordinate system to Cartesian coordinates. So let's take a look at an alternative way, rather than using cylindrical coordinates, to use angles and distances to replace Cartesian coordinates in 3 dimensions. Now, for the second coordinate system, we're once again going to start off with our basis as polar coordinates, with ordered pairs r theta on the polar plane. This time around, though, we're going to kind of break free of our desire to just throw in axes that are always orthogonal to some previous set of axes. We're not going to just add z in this time. Now, it's going to feel a little bit unnatural to kind of break free of those orthogonal axes, but we're going to use something else that is also fairly natural, and that is just angles and distances. And that's really all we need here. Rather than just having a elevation above the polar plane, we're going to take a look at another angle. To try to imagine this other angle, think about being at the origin and looking at a point in 3 dimensions. Well, if we had a reference line, that's our x-axis or our standard polar axis, then we would just turn around to face the object and give us the angle of theta, depending on how far we've rotated counterclockwise around our conventional z-axis. And then we just have to figure out how far our gaze has to go up or down from horizontal. What we choose to do is start our gaze straight up, and if the point's not there, start looking downward towards the horizon, and that will give us a second angle. So rather than using theta, this second angle is going to be the angle phi. Now, and there's I say phi, other mathematicians, other scholars might say phi. It's the same in Greek letter. I just kind of think of phi as in philosophy, which has also Greek roots. So this angle phi, measured from perfectly straight up, can only go as far as pi radians, or 180 degrees straight down. With those two angles, thinking about how far you need to rotate your gaze away from the x-axis counterclockwise around the positive z-axis, and then how far we need to rotate our gaze down from the positive z-axis. The only thing that remains is the distance from the origin. Now, here we have another Greek letter. Rather than using r, which gets a little confusing between cylindrical and polar coordinates and spherical coordinates, we'll use the Greek letter for r, which is rho. It kind of looks like a P with a little bit of a tail on the end. That gives us a new coordinate system, which is called the spherical coordinate system. We have ordered triples, rho, theta, and phi. So rather than r, theta, and z in cylindrical coordinates, rho is a distance measured directly from the origin, not a distance measured from the z-axis. Theta is the same between cylindrical and spherical coordinates, but rather than use z, we have this new parameter or variable phi. A good way to remember the meanings of these three components is that theta determines a vertical half plane. Any value of theta is just simply how far you need to rotate your body around to view the point from the origin. Remember, always going counterclockwise around our z-axis. Phi measures the angle from the positive side of that z-axis. And then rho is a simple distance. And typically, we have theta from 0 to 2 pi, since that will take us one rotation around the circle. We have phi from 0 to pi, since that takes us from the positive z-axis to the negative z-axis. And typically, distance is positive or equal to 0. Now, if this system seems a bit strange, actually it's pretty common and we use it all the time. You simply just need to think about GPS, or latitude and longitude. Here's our positioning system across the globe. We have a couple reference points. We have our equator and we have the prime meridian. Then we measure points on the Earth as just being angles away from those two reference points. We have angles away from the equator measured in degrees from 0 degrees north to 90 degrees north, or 0 degrees south to 90 degrees south. Our system of spherical coordinates can be a little easier. Rather than having to specify north or south, we just measure from the North Pole all the way down. That gives us from 0 to 180 degrees, or 0 to pi. That's our angle phi. We also measure away from the prime meridian, which is kind of an arbitrary line that we just drew through the center of what was kind of the biggest country in the world at the time. From that line, we measure angles west or east. We can have 20 degrees west, or we can have 60 degrees east. So you can see the general similarities between spherical coordinates and our latitude and longitude system. Well, just the difference being that we don't measure degrees west or east, degrees north or south in spherical coordinates. We just let everything start at 0, and we have one angle make a full 2 pi revolution, and we have our other angle go from 0 to pi. The other difference is that we also have rho, which doesn't really play a part in latitude and longitude, but you could think about that as being elevation in our standard GPS coordinates. Your GPS location isn't just degrees north, degrees west, but it's also how far above the Earth's surface you are if you're flying an aircraft or if you're hiking. That's rho. So the three parts put together put you in a position in three-dimensional space. Now, how do we convert between these spherical coordinates and our standard Cartesian coordinates? Well, here's the graph of our spherical coordinate system again. And it might actually be easier just to convert between spherical coordinates and cylindrical coordinates, and then borrow those conversion formulas so that we can convert right back to Cartesian coordinates. Remember that theta puts us onto a vertical half plane. Now on that half plane, you can see that there's a beautiful right angle triangle. Here I've just shaded that in pink. And one side is the positive z-axis. The hypotenuse would be rho, and that gives us our remaining side, here indicated as that purple arrow. You might notice that the length of that third side is precisely what we call r in cylindrical coordinates. And so r is equal to rho sine phi. If we plug that into our conversion formulas for the cylindrical coordinate system, then we can come up with some conversions between spherical coordinates and Cartesian coordinates. That gives us x equals rho sine phi cosine theta, and y equals rho sine phi sine theta. And using that same triangle, we can see that the z coordinate of that point is equal to rho cosine phi. Now, we have a few other conversion formulas that are going to be very handy. You can see rho is simply just the distance measured from the origin. And from our distance formula, we can come up with a conversion formula that x squared plus y squared plus z squared equals that distance rho squared. Since theta here has the same meaning as cylindrical coordinates, we still have the conversion formula that tangent theta equals y over x. And using a couple of triangles, we can see that tangent of phi is equal to the square root of x squared plus y squared. That's just simply r in cylindrical coordinates over z. That's using that triangle again. Now, as you can see, these formulas are a little bit more complicated. The conversions between spherical and Cartesian, it's not quite as easy. So this system had better be worth it for something, you would think. Obviously, it works for latitude and longitude, so it does have a useful purpose. Let's see what kind of graphs are a lot easier to express in this coordinate system versus maybe cylindrical or especially Cartesian coordinates. As a first example, let's just take a look at the equation where rho is constant. I'm calling this constant radius because, well, rho is essentially a radius. It's a distance measured from the origin, and it can be rotated in both theta and phi. So that creates all possible directions. This gives us a constant distance from the origin, and we should recognize that hopefully pretty quickly as being a sphere. It may not come as much of a surprise that expressing a sphere in spherical coordinates is the best possible option. It just needs to be centered at the origin, otherwise it does get a little bit more messy. Now, I won't spend too much time on this next example. If theta is equal to a constant, rho can be any value, let's say, greater than or equal to 0, and phi can be any value, let's say, from 0 to pi. Well, this is basically the same thing as letting theta equal a constant in cylindrical coordinates. So we've already covered that. That gives us a half plane. But what is a little bit more interesting is when we let phi be a constant. Let's suppose phi is equal to some constant c, and rho could be any real number. We'll let it be negative for this particular example. And let's say that theta is, again, our classic from 0 to 2 pi. Let's check off some of the boring examples first. Phi is equal to 0, then that would point in the direction of the positive z-axis. And letting rho be either positive or negative, that just gives us the z-axis. That would just be the equation of a line. Similarly, if phi is equal to pi, that's just going to be the negative z direction, and letting rho be positive or negative, that again just gives us the z-axis. So that's not super interesting. The last kind of boring example is if phi is equal to pi over 2. Well, in that case, that actually is perpendicular to the z-axis, and that will give us the set of points forming the xy plane. With those cases out of the way, let's suppose that phi is some value between 0 and pi, non-inclusive, and also not equal to pi over 2. Well, in that case, for any particular value of theta, that's going to give us a line passing through the origin, forming that angle with the positive z-axis. Then, if we let theta range from 0 to 2 pi, we could take this line with that particular angle and revolve it around the z-axis. Now try to imagine what that kind of shape is going to give us then. After one full revolution, that gives us a cone. And we have both our inverted cone as well as a right side up cone, depending on whether rho is positive or whether rho is negative. This should hopefully illustrate a couple strength of spherical coordinates. Obviously, spheres centered at the origin are best done in spherical coordinates. It just makes sense. But it's also another good coordinate system for looking at cones. Specifically, like cylindrical coordinates, these are cones that are centered on the z-axis with the vertex at the origin. Okay, let's take a look at Maple and make sure that you know how to plot in spherical coordinates as well as cylindrical coordinates. Remember that this parameter chords equals cylindrical was the key to making sure that Maple knew which system we're using, but you also had to be very cautious about which of the two domains to specify first. theta and r was crucial to getting cylindrical coordinates correct. Let's do the same thing with spherical coordinates now. Here I'm going to plot rho equal 4. And you notice I'm not actually typing in that rho equals. Plot 3D, when using coordinates equals spherical, is going to expect that your surface is going to be expressed in the form of rho equals some expression involving thetas and phis. For other particular kinds of surfaces, if it's not in that form, well, we'll see if we can take a look at those in the future. Here I have theta first, same as cylindrical, so that's kind of convenient. And then I have phi next instead of r. Coordinates equals spherical is going to ensure that this is graphing in the correct coordinate system. And sure enough, that just gives us a sphere of radius 4. To see that that is actually centered at the origin, we could always change the axes so you can see that they should be just kind of poking out the 4 different quadrants there. Once again, you can just see how nice these graphs actually show up in Maple versus trying to do them by hand. Or even worse, if you try to graph the equation of a sphere using Cartesian coordinates, it may not come up with kind of these nice smooth edges. These coordinate systems are very well designed for plotting something that has some kind of circular rotational symmetry. Cylindrical is really good if it's simply just rotated around the z-axis. Spherical coordinates are particularly good if we have something that is rotated around the z-axis, but also has some kind of rotational symmetry from sort of the positive z-axis down to the negative z-axis as well. So with these two coordinate systems now, you can really get kind of into some interesting shapes. And we're not going to necessarily use them very frequently, but when we do want to take a look at surfaces of one of these kind of particular shapes, it's going to help us with calculus later on, looking at things like volume, for instance, or maybe taking a look at mass of a sphere if the density varies from one spot to another inside the sphere. That's going to be much further ahead in the future, but it's always good to have an idea of these two coordinate systems well in advance. So thanks for watching, and I'll see you in the next video.